So today we have sort of three objectives. We're going to review what we've learned about linear transformations. We're going to talk about the space of linear transformations from a vector space to itself, and some special things we can say about that case. Talk about null spaces and kernels. Null spaces, also known as kernels, and injective and surjective maps, and how that relates to linear transformations. So let me begin by reminding you of some basic definitions. So suppose V and W are vector spaces over a field F. A function, which is a function of the sets from V to W. It's called a linear transformation. If for all A in the field and for all pairs of vectors in the domain, and let's just do this version, f of AU plus V equals A f of U plus f of V. Now there were three equivalent versions of the definition of linear transformation. This one, the one with additivity and homogeneity, and four. The one with another coefficient, and the one with a long list of things. And if you haven't done that yet, you should convince yourself that those are all equivalent. Now, this definition implies that f of the zero vector in one space is the zero vector in the other space. Some of you included that in your definition, which is fine, but you don't need it. We then talked about the vector space of linear transformations. Part of your homework is to prove that it's a vector space. And it's denoted by various things. In this book, it's usually called L of VW. And I mentioned some other names, like HOM of VW, which stands for homomorphisms. That is, it's the structure-preserving map in whatever setting we're talking about. Here, linear vector spaces and linear transformations. So it's a homomorphism of vector spaces from V to W. And at least in the case of finite dimensional vector spaces, we'll talk about what this means otherwise, but I'll also introduce this notation, V star, the dual space, right, V star tensor W. And part of the reason that I want to familiarize you with these other names is depending on the area that you go into, you may never see this particular notation. Again, you'll see different notations for the space of linear transformations. In the kind of math I do, you'll see these two definitions and never this one. So, or these two names and never that one. This vector space of linear transformations has addition and scalar multiplication and the zero. If the addition is defined by f plus g, so f plus g in this space, L of VW, the addition of two linear transformations, is defined by application of this function to some vector v by whatever f was applied to v plus whatever g was applied to v. And the addition over here happens in W. So we're inducing the vector space structure on the space of linear transformations from the vector space structure on W. And it had scalar multiplication the scalar multiplication also induced, that is, it's defined to be the vector AF for A in the field is defined by the application of this function to V as A times whatever f of V was. And it's just as the addition was happening in W over here, the scalar multiplication is happening in W over here. And then we had a 0 vector, which, like every other 0, is denoted by 0. If we want to decorate it, we can put the name of the vector space down here. And that was the vector, as we figured out in class, that simply eats any vector and spits out always 0. And this 0 would be the 0 in W. And you can show, as I ask you to in the homework, that this plays the role of the 0 vector. That is, it's the additive identity in the vector space of linear transformations. So the next thing we observed is that linear maps, being functions, can be composed when they match up correctly. So if I have a linear map F from U to V and another linear map G from V to W, so F goes from U to V and G goes from V to W, I can construct from them G composition F, which is a map from U to W. We took kind of a guess and check approach. The composition we defined it pointwise. That is, we just use the definition of composition of functions. And because we define it that way, we then had to check that the result was in fact a linear transformation from U to W in that case. Whenever you see a notion of composition, there's two questions you should ask yourself about it. Is there an identity, and is it associative? We talked about why those things are true. So there's an identity linear transformation. That is, for any vector space V, there's a special linear transformation in the space of linear transformations. I should say, for all V, there exists an identity linear transformation in the space of linear transformations from the vector space to itself. And that plays the role of an identity. But because we have to worry about varying domain and codomain, this isn't the kind of identity where one identity works for every function, right? Each vector space has to have its own identity. So if I take a function f that goes from U to V and another function g that goes from V to W, we need that there are left and right identities. So in other words, here's my f from U to V, and I have an identity. The identity on V composed with f is equal to f. And on the other side, my G goes from V to W. So I put the identity for V over here, and this would say G times the identity for V is equal to G. And we chose this symbol for identity in our schematic in order that it solves the same equation. If I wanted, so this is a left identity for F. I wanted a right identity for F. What would it be? What's the name of the identity that goes on the other side? F composed with identity, what equals F? U, that's right. So the left and right identities in this case are different if F does not go from a vector space back to itself. This composition is associative. So if I have F, G, and H, U, V, W, Z, it's true that H composed with G composed with F equals H composed with G composed with F regardless of how I parenthesize. And there's another feature of this schematic that doesn't even really have a way of distinguishing between those two things, so that associativity holds here. Look, can anyone tell me there's a name for something of this type where we have a bunch of sort of objects or like vector spaces, we have a bunch of arrows or maps between them, things that connect them, and there's a composition law, it has an identity, and the composition law is associative. It's an algebraic object of a kind. Anyone know what the name of it is? At least one person actually wrote it on the exam. It's called a category. Look up the definition of that. Another example of a category is this one with finite sets and relations that we're talking about. It has a similar structure. There's an identity, it's an associative composition, and so on. One other thing we observed about this composition for vector spaces, which is not true for general categories because they don't have always a notion of addition, is that with the addition in the space of linear transformations, composition is associative, is distributive. By that I mean G composed with F plus H equals G composed with F plus G composed with H, and G plus F composed with H equals G composed with H plus F composed with H, when that makes sense. I.e. when F and H both go from some space to another so that you can add them, and G eats whatever the output of that is. Takes it. So let's say when we have G here, and here we could put F or H, and maybe this is U, V, W. Okay. Then it makes sense to add F and H because they have the right type. And similarly, that's for this picture, and similarly for that picture. So it's distributive when it makes sense. Now, all this simplifies a bit to something more familiar when we consider only vectors, only linear transformations from a vector space to itself. Right? Because then I don't need this business about when that makes sense. I don't need to worry about whether or not the domain and the codomain of my linear transformation match up. So this thing has a special name, like many things do. So you'll sometimes see this called endomorphisms, endomorphisms of a vector space, V. So what does this mean? If this other notation hom meant homomorphisms or morphisms, structure-preserving maps from V to W, the prefix end, or endo, if you've taken any biology classes, you probably read into it, means like something that kind of folds in on itself. Right? Endothelium, stuff like that. So this means a structure-preserving map that flows back, and folds back onto itself, or a map from V back to V. And this thing, because I don't have to worry anymore about whether or not the domains and codomains match up, about these compatibility conditions in end V, I could say a little bit more about it as an algebraic object. So let's make some observations about it. Well, we know that already, from your homework, that this thing is a vector space. It's a F vector space. If F was the field over which V was a vector space, in particular, it's an additive abelian group. And we know how to do addition and scalar multiplication, and we have a 0, right? But it has something new. It has a multiplication now, which is the composition of functions. Composition of multiplication. Which is given by composition, right? And this multiplication, if I have any f g in my LVV, and I can take both fg and I can take gf. Those things both make sense. They're both maps from V to V. All of the domains and codomains match up. And this multiplication is associative. FGH equals FGH, regardless of how I parenthesize. So because we have to do so much composition of linear maps, I'm going to start dropping the little circle in between to indicate composition, because that's how you'll see it other places. So it's associative. There's an identity. What's the identity called in this case? It's ID. And it's an identity on both sides, right? For all f in this space of linear maps from a vector space to itself, ID times f equals f times ID. Right? Two-sided identity, and it's distributive. That is fg plus h equals fg plus fh, and f plus g h equals fh plus gh. And now I don't have to say when that makes sense, because as long as f, g, and h are all maps from some vector space V back to itself, then all those things make sense, right? But it is not commutative. That is, although they both make sense, in general, fg and gf are not equal. order in which we multiply matrices matters. There's also a name for this structure, something which has all these properties. Anybody know what that is? Let me give you two examples. Which are commutative. The integers and polynomials in one variable. So those are commutative examples of this structure, where I have multiplication, but I don't have multiplicative inverses. And I have addition. And so these are all examples of rings you've seen in a previous class, like 311. These are commutative rings, and the one we've just described is a non-commutative ring. I can add, I can multiply, it's distributive, it's associative. And we'll make use of that structure because you can think of it as similar to a field. A ring is similar to a field, but I don't have inverses, like integers, right? The integers I can do plus and I can do times, and they behave the same way as they do in the reals, but I'm not allowed to take multiplicative inverses. I can't go one. There's no 1/2, to invert 2. Similar structure, except that it's non-commutative. Now, this structure will become important later because this space of linear transformations from a vector space back to itself is going to be probably the main focus of kind of the second half of the class, where we're concerned with spectral theorems and understanding what we can say about the structure of such linear transformations. Another way of saying that is finding normal forms for matrices, properties of invariance of matrices. And some of that we'll be able to derive by thinking about this as an algebraic structure. Okay. Another thing to recall that we can define a linear map, linear transformation, by saying what it does on bases. On a basis. I encourage you to think about that a little to see that that's kind of enough to define it, and I'm also free to do whatever I like to the bases. And the reason for that, I'm going to remind you, is that suppose I have a vector space V, and it has basis V1 up to Vn. Any vector in V can be written V as a linear combination of some coefficients AI times the bases in the vector, the vectors in the basis. And if I apply f to this arbitrary v, by linearity I can apply, it equals what I apply here, and by linearity I can push it through the sum, and I can push it through the scalar multiplication. And so I've written it in terms of these things, each of which lies in the codomain. F goes from V to W. And so where I send any vector is determined by the fact that it's linear and telling you where it sends the basis. So that's a very restrictive assumption, right? I mean, it tells you that you have any function on, say, R3, R2, any function on the blackboard, all I have to do is tell you where it sends of two independent points. I get two vectors that form a basis for that blackboard. I tell you where it sends those two things. Where it sends everything other point on the blackboard is fixed for you. Gives you a sense of how restrictive it is to say something is a linear transformation. It's very restrictive. Question for you. In this case, assuming that V1 up to Vn is a basis, is this f of V1, f of Vn, a basis for the image space, for the codomain? Is it? What do you think? Yes or no?
Like not necessarily?
Yeah, that's a good answer. Not necessarily. So no, or not necessarily. So towards the end of today, or first thing next time, we'll talk about when that is true. Let's give an example of when it's not true. Suppose I have a linear transformation, goes from R2 to R3, and let's have bases UV for R2 and XYZ for R3. First of all, you can tell that it's not going to be a basis in this case. Why is that? The image of f of u and f of v are over here, but they couldn't be a basis for that space. Why is that? Yeah, that's right. Because we know that all bases have the same length. The basis for this space has to have 3 elements. This only has 2 elements, so it couldn't possibly be a basis. Okay, so there's a counterexample. And by the discussion we're talking about earlier, we can define, a linear transformation by telling you where it sends u and v. So suppose it sends u to a1x plus b1y plus c1z, and it sends v to some linear combination a2x plus b2y plus c2z. xyz was a basis for R3, so I could write any vector in R3 this way. And I could collect these coefficients into a matrix. It would look something like this: a1, b1, c1, a2, b2, c2. And probably later this week or next week we'll finish this off. But the idea is that, well, I just tell you where it sends its every element of the basis in terms of elements of the other basis, and that's enough to define that map. So since we live in R3 approximately, and the blackboard is R2, so what do those look like? Linear transformations from R2 to R3. How would you describe, say, the image of a linear transformation from R2 to R3? It's just some plane. Yeah, some plane in space. Has to have the same 0. It has to send 0 to 0. But so whatever 0 you pick for R2 better be the same 0 for. Okay. It's just some plane in R3. Okay. So that's an example. Two other examples that are important, which are not sort of this form, are from calculus, differentiation and integration. So differentiation you could think about as a linear transformation from polynomials to polynomials. I mean, it works for other functions, but it's sort of nice for polynomials. So let's restrict ourselves to that for a second. And then the derivative of a polynomial, p of x is dp of x dx, or p prime of x, depending on your notation. And to say that it's linear is to say that d of two polynomials, f plus g, I guess I should put the x there, is equal to df of x dx plus dg of x dx. So you remember that fact from calculus. And similarly, d of af of x is a df of x dx. In the other direction, I could do integration in various flavors. Let's say the one that sends, again, a polynomial, and it sends it to, say, a real number. Let's make a real polynomial. Let's call this map I, and that would be the one that takes a polynomial p and spits out the integral from 0 to 1, p of x dx. Such a thing is also linear, respects addition and scalar multiplication of polynomials. So let's get back now to talking about null spaces and kernels. So let me remind you, and then we're going to link them to some other things. So definition, suppose I have a linear transformation from a vector space V to a vector space W. The null space, or kernel, denoted null of f, or kernel of f, using the mostly null of f, is just the set of all vectors in V that f sends to 0. Set of all vectors in V that f sends to 0. Now, in this category of vector spaces and linear transformations, we don't really like sets. We prefer that all our sets be vector spaces. So the first thing we're going to do then, the first thing we want to know is this set, which is somehow associated to a linear map, is it actually a subspace? Is it a vector space? So the answer is yes. So suppose we have a linear transformation from V to W, then the null space of F is a subspace of V. Let's do the proof. Well, we have a subspace criterion we can use to prove things like this, right? First of all, we'd like 0 to be in the null space. Well, that's true because f of 0 is 0. So 0 is something which gets sent to 0. That's V, that's W. So 0V is in the null space. That's supposed to be a subspace of V. So we first check that the 0 of V is in there. Second, we want to check that it's closed under addition. Suppose I have U and V, which are in the null space of F. F of U plus V by linearity of F is F of U plus F of V. Since U and V are in the null space, that's equal to 0 plus 0. And by additive identity in W, that's the 0 vector. Great, so it's closed under addition. And we also want to check that it's closed under scalar multiplication. So if A is in our field, we want to know if F and U is in the null. F of AU by linearity of F is equal to A F of U. This is equal to 0. And A times 0 is 0. Okay, so it's closed under addition and scalar multiplication. Great, so null F is not a foreign concept. It's a vector space. I want to avoid talking about things that aren't vector spaces, right? So the last thing I want to talk about today is injectivity and surjectivity. There's a couple questions about this on your homework, so you had to read ahead a little bit, but let's talk about it in case you haven't looked at that yet. So injective and surjective are defined for functions. Function f from a set A to a set B is injective if whenever for all AB in the set A, whenever F sends A and B to the same place, whenever F of A equals F of B, that implies that in fact A and B were equal. So this equality is happening in the set B. This equality is happening in the set A. And it's surjective if given any element in the codomain, given any b, little b and b, there exists something in the domain, some element of the domain, such that that element maps to b, little b under F. So we can hit every element in the codomain by applying F to something in A. Okay. So suppose we have three sets, A, B, and C. And I have two maps, F and G. And I think about F, G, and G composition F. First apply F, then apply G. F could be injective or surjective. G could be injective or surjective. And I'd like to know, what can we say about their composition? Is it injective, surjective? Well, we can't tell from that information. But using these definitions. So how about if I compose two injective functions? It's injective. How about if I compose two surjective functions? Surjective. How about if I compose an injective and a surjective function? This one. Let's make a picture. So here's A, here's B, here's C. Let's make F injective. And let's make B surjective. Or G surjective. So that's F and that's G. So how about G composition F? Injective, surjective, neither. Oh, I need to add something, right? Wasn't even functions. So how do I get to this point? What do I choose in A? Nothing, right? So it's not surjective. How about injective? It's neither, right? Okay, so we don't know based on that information. How about this guy? Compose a surjective function and an injective function. So let's make some new functions. I don't know. Something surjective. Something injective. Injective, surjective. Okay, so again, this is going to be neither. Don't know. Can't tell from that information what it is. Okay. That's just to review those two concepts and how they, what happens under composition of arbitrary set functions. Now, as I was saying, linear transformations have a great deal of structure. It's very restrictive to say something is a linear transformation. And so when we apply the concepts of injective and surjective to linear transformations, we're going to get a lot of things collapsing into one. So we're going to get a lot of restrictions. For example, proposition, a linear map from a vector space V to a vector space W is injective if and only if its null space is equal to the 0 vector space. So proof. First, suppose F is injective. INJ and its surge, it's going to be the abbreviations. Suppose F is injective. Well, we know for sure that the 0 vector is in the null space of F. Suppose I look at some other vector, V in null of F. F of V is equal to 0 because it's in the null. But F of 0 is also equal to 0. So by injectivity, we have two things being mapped to the same element by an injective function. They must be equal. Therefore, the null space is just 0 because everything is equal to 0. On the other hand, suppose the null space of F is equal to 0. And I take two elements uv in my vector space, and they have the same image. F of u is equal to f of v. Then f of u minus f of v is a way to write 0. And by linearity, so we've mostly used linearity in the other direction, but we can also use it to pull f out. That's equal to f of u minus v. That means that since f of u minus v is equal to 0, u minus v must be in the null space of f. But there's only one thing in the null space of f, namely 0. U minus v equals 0, and u equals v. And therefore f is injective.